हेलो माय डियर मैकेनिकल चैंपियंस, हाउ आर यू ऑल? व्हाट्सअप, कैसे हैं सब लोग? क्या आप तक मेरी आवाज पहुंच पा रही है? कैन यू गाइज हियर मी? प्लीज गाइज डू जॉइन मी फास्ट एंड दोज हु आर हियर प्लीज रेस्पॉन्ड थ्रू द कमेंट सेक्शन इफ माय ऑडियो एंड विजुअल क्वालिटी आर फाइन. Can you guys hear me? Yes, Gaurav, Vinay, welcome guys, welcome to the session. So as you can see, today we will be discussing the most important formula and some questions from the topic of convection mode of heat transfer as well as radiation mode of heat transfer. The session is important for all the mechanical aspirants who are sincerely preparing for ISRO 2023 exam. As you all know that there was an update yesterday regarding ISRO 2023. You can change your center. So there is some movement in the official website for the ISRO. So you can expect the dates to be announced for the examination very soon. So please keep your preparation in the next gear because you will be having very less time to revise your fundamentals to crack the examination. So for that only we have brought this series where we are discussing the important formula as well as some question practice. So shall we start convection and radiation? Before I start my session, let me quickly introduce myself for those who are attending the session for the very first time. My name is Chandrasekhar, नाम तो सुना ही होगा. I am mechanical engineering graduate from IIT Delhi. I have also cleared engineering services examination conducted by UPSC. I had worked in Steel Authority of India Limited for a couple of years, and from last 10 plus years, or you can say from last 11 years, I am completely into teaching, guiding the students who are preparing for various competitive examination. All right. So with my knowledge, experience and my analysis, I can guide you in the right manner to crack the examination. And I am quite comfortable in the mentioned subjects of mechanical engineering, fluid mechanics, thermal engineering, industrial, as well as the heat transfer. And if you have any doubt, anything to discuss regarding any of the subjects or anything in general, you can always connect with me through the mail ID, which is there on the top of the screen. And it will always be better if you join me on the Telegram. Mechanical by Chandrasekhar. The link is also shared below. So please guys, do not forget to like and share this session so it reaches to all the students, all the sincere students who are preparing to crack ISRO 2023 exam. All right. So shall we start? On coming Sunday, there is a scholarship test, national level scholarship test for GATE exam conducted by BYJU'S on 6th of August from 9 a.m. till 9 p.m. So please do register yourself. It is completely free, and to register for this scholarship test, the link is mentioned in the description box. Good morning, Pajal World. Welcome. Once you become part of this scholarship test, you will be able to check your preparation level as well as based on your performance in the scholarship test, you will be able to avail the discount in our various paid courses. And we always recommend the students to take the paid courses because if there is a guidance available, then you should avail that because it is your career which is at stake. So you should not leave a single stone unturned to clear these examinations. So you can clear the examination without any guidance as well, but it will require more efforts, it will require more time. So to crack the examination with the best possible score, with the minimum time and the minimum of efforts, you should have the proper guidance, and that is always beneficial for competitive examination like GATE and other PSUs. So let us start with the question number 1. Question 1 on your screen. Formula for convective heat transfer coefficient is, which of the following options is correct? As you should know that convection is called as combined effect of conduction plus bulk motion of the fluid. Convection is the combined effect of conduction as well as bulk motion of the fluid. There is a conduction in the no slip region. There is always a conduction in the no slip region if there is a surface and there is a fluid kept over the surface. There is a thin region near the surface where the velocity is same as the surface velocity. The region is called as no slip region. In the no slip region, because the fluid motion is 0, the velocity of the fluid is equal to 0. The velocity of the fluid is same as the velocity of the surface. So the mode of heat transfer will be conduction in the no slip region, and in the bulk fluid the mode of heat transfer will be convection. So Q can be written as, by using the Fourier law, H into area available for convection into bulk temperature difference, that is Ts minus T infinity, is equal to, if we apply the conduction equation or Fourier law, this is Newton's law of cooling. HA delta T is Newton's law of cooling. If we apply the Fourier law minus thermal conductivity of the fluid into area perpendicular to the direction of conduction into temperature gradient in the fluid at y is equal to 0. Q will remain constant as long as the system is in steady state and no heat generation. If the system is in steady state and if there is no heat generation. So if you equate these two formula, if you are going to equate these two formula, then you will get the expression for convective heat transfer coefficient. The unit is watt per meter square Kelvin or watt per meter square degree Celsius. Option B is the correct answer for this one, isn't it? Option B. I hope this is clear. Option B will be the right answer. And how to get the value of dt by dy at y is equal to 0? If we know the temperature profile. Charan Cherry, it is only the notation. Whether you use the notation capital Q or small q, it does not matter. So small q is the rate of heat transfer. The unit of small q is joule per second or watt. Right? So B is the right answer. Yes, Vinay, Pagel World. Well done, guys. Keep on sharing your answer. Everyone, please. How to get the value of dt by dy at y is equal to 0? If we know the temperature profile in the fluid, by differentiating it, we get dt by dy. And what is delta T? Delta T is equal to Ts minus T infinity if Ts is greater than T infinity. Now the convection can be of two types. What are the two types of convection? Can you let me know? Convection is of two types. One is called as forced convection, or we can call it as artificial convection. The another is called as free or natural convection. Forced and free. Yes, forced convection and free convection, or we can call it as artificial convection and natural convection. In artificial convection, the parameters governing the flow based on the fluid motion, convection can be divided into two types. What are the governing parameters? One is the pressure gradient. the variation of pressure will develop the inertia force. The variation of pressure will develop the inertia force. These are the two factors governing the forced or artificial convection. Wherever free and natural convection is governed by density gradient, and due to density gradient, buoyant force develops, which drives the fluid motion. So these are the two types of convection, right? And in case of forced convection, or artificial convection, we can say there are three dimensionless numbers. Nusselt number is a function of Reynolds number multiplied by a function of Prandtl number. In case of forced convection, Nusselt number is derived by, or is the function of Reynolds number multiplied by a function of Prandtl number. What is the Reynolds number? The ratio of inertia force by viscous force, rho VL by mu. The Reynolds number is ratio of inertia force by viscous force. What is Nusselt number? What is the Nusselt number here? Nusselt number is the ratio of conductive thermal resistance in the fluid to the convective thermal resistance in the fluid. The ratio of conductive thermal resistance to the convective thermal resistance is the Nusselt number, or we could have written as Q convection upon Q conduction in the fluid, because the convection is the combined effect of conduction and bulk motion. So the ratio of heat transferred due to convection to the ratio to the heat transfer due to conduction is called as Nusselt number, and each is given by HL by KF. What is the difference? There is another number which is having the same type of expression. The ratio of conductive thermal resistance to convective thermal resistance. हाँ पार्थ मैं समझ सकता हूं, but revision is important, because ISRO will not ask you all the numerical questions. There are possibilities to have the theoretical question. What is the Prandtl number? What is the Prandtl number? Yes, Biot number is also the ratio of conductive resistance to convective resistance. But the only difference is conductive resistance is for the solid and the convective resistance is for the fluid. What is the Prandtl number? What is Prandtl number? It is the property. Prandtl number is the property of the fluid. Yes. So Prandtl number represents, the next question is, the Prandtl number represents MSQ. It is MSQ. It is MSQ, Vinay. The Prandtl number is the ratio of kinematic viscosity or momentum diffusivity to thermal diffusivity, or we can write mu by rho upon alpha is K by rho C. So Prandtl number is dimensionless number and it is the property of the fluid. And why it is defined? So the answers are B and D. Answers are B and D. And it is the connecting link between velocity profile and temperature profile. Prandtl number is the connecting link between velocity profile and temperature profile. For natural convection or for natural convection, or for free convection, we can say Nusselt number is a function of Reynolds number will be replaced by Grashof number into a function of Prandtl number. So Prandtl number always connects the velocity profile and temperature profile, or we can simply say Prandtl number is the connecting link between fluid mechanics and heat transfer. All right. So B and D are the correct answer for this one. B and D will be the right answer for this one. Now from here, the convection or the forced convection can be further divided into two types. To make our analysis simple, we divide the forced convection in two types. One is the external forced convection, another is called as internal forced convection. One is called as external forced convection, another is internal forced convection. Let us talk about the external forced convection. What is the meaning of external forced convection? When the fluid is flowing over a plate, flow over a plate is an example of external forced convection. The analysis will be done by boundary layer theory. The analysis of the external forced convection is done by boundary layer theory. So there are some important formula you should remember. One is laminar boundary layer. When the boundary layer is laminar, when do we have the laminar boundary layer? Reynolds number or local Reynolds number, that is rho u infinity x by mu, or we can write it as u infinity x by kinematic viscosity, if it is less than 5 into 10 to the power 5. The boundary layer will be laminar when the Reynolds number is less than 5 into 10 to the power 5. For this, the velocity boundary layer thickness is given by 5x upon under root of Rex. The velocity boundary layer thickness is given by 5x upon under root of Rex. So velocity boundary layer thickness is directly proportional to root x, isn't it? The next formula is the ratio of del V by del T. The ratio of velocity boundary layer thickness to the thermal boundary layer thickness is given by Prandtl number to the power 1 by 3. And from here we can say if the Prandtl number is less than 1, then delta V will be less than delta T. If the Prandtl number is equal to 1, then delta V is equal to delta T. If the Prandtl number is greater than 1, then delta V is greater than delta T. Delta V is the velocity boundary layer thickness and delta T is the thermal boundary layer thickness. These are important formula for laminar boundary layer and laminar boundary layer for flow over a flat plate. If we draw the boundary layer, the growth of boundary layer over a flat plate, so it will be something like this. In laminar region, there will be two boundary layers. In laminar region, there will be two boundary layers. But in turbulent, it will be a single. Delta V is equal to delta T. In turbulent boundary layer, here in laminar boundary layer, one curve is A, another is B. So if Prandtl number is less than 1, then we can say B is the velocity boundary layer. If Prandtl number is equal to 1, then A is equal to B. If the Prandtl number is greater than 1, then A will be velocity boundary layer. Do you understand it or not? Do you guys agree or not? Isn't it? Now the another formula is local drag coefficient, that is tau naught upon rho u infinity square by 2. That is called as local drag coefficient, that is given by 0.664 upon under root of Rex. So we can say Cfx is proportional to x to the power minus 1 by 2. Cfx is inversely proportional to x to the power minus 1 by 2. That is called as local drag coefficient or local skin friction coefficient. It is called as local drag coefficient or local skin friction coefficient. and CD, average drag coefficient, is twice of CF at x is equal to L. The average drag coefficient is twice of, this is called as, it is not a function of x. That is called as average drag coefficient. This is called as average drag coefficient. Next formula is the local Nusselt number, that is Hx into x by Kf is equal to 0.332 Reynolds number to the power 1 by 2 into Prandtl number to the power 1 by 3. So from here we can say Hx is also proportional to x to the power minus 1 by 2. Hx is also proportional to x to the power minus 1 by 2. Average h is twice of h at x is equal to L. And average Nusselt number is twice of Nusselt number at x is equal to L. These are average convective heat transfer coefficient. Yes, Naruto, which last point you did not understand? Are you talking about this? Which point you are talking about? So these are the standard formula you should memorize for laminar boundary layer over a flat plate. Whenever the Reynolds number is less than, whenever the Reynolds number, are you talking about this? A and B. In laminar boundary layer region, the thermal boundary layer and velocity boundary layer will be different. Whenever there is a flow over a flat plate, the growth of velocity boundary layer and the thermal boundary layer is different. So when it will decided by the Prandtl number, when the Prandtl number of the fluid is less than 1, whenever the Prandtl number of the fluid is less than 1, example mercury is having Prandtl number less than 1. So in case of mercury, the growth of velocity boundary layer will be lesser compared to the growth of thermal boundary layer. So the upper curve will be thermal boundary layer and the lower curve will be velocity boundary layer. Are you getting it? Whenever the fluid is having Prandtl number is equal to 1, Prandtl number is the property of the fluid. For an example, air near atmospheric condition. Naveen, Prandtl number is the property of the fluid. It is not related with the flow. Prandtl number is not equal to 1 in turbulent flow. The Prandtl number does not depend on the type of the flow. Prandtl number is the property. There are fluids whose Prandtl number is equal to 1. There are fluids whose Prandtl number is less than 1. There are fluids whose Prandtl number is greater than 1. For the fluid having Prandtl number equal to 1, it means in laminar region there will be equal growth of velocity boundary and thermal boundary layer. So A and B will be equal. Both velocity boundary layer thickness and thermal boundary layer thickness will be same. There are fluids whose Prandtl number is greater than 1, like water. For water, the Prandtl number is around 7. So, for water, if the water is flowing over the flat plate and if the boundary layer is laminar, then we can say the growth of velocity boundary layer will be more than the growth of thermal boundary layer. So, curve A will be represented by velocity boundary layer and B will be represented by thermal boundary layer. So Prandtl number has nothing to do with the type of the flow. But let me tell you, in case of laminar flow, the flow is organized. The flow is such that the fluid particles are moving one over another, sliding one over another. So that is why there is a different growth of boundary layer. There is a difference in the growth of velocity boundary layer and thermal boundary layer. But whenever the flow becomes turbulent, the mixing of the fluid dominates. In case of turbulent flow, it is disorganized. Mixing starts dominating in case of turbulent flow. Due to mixing of the fluid particles in case of turbulent flow, there will be equal amount of growth of velocity boundary and thermal boundary layer. So Prandtl number is significant only in case of laminar boundary layer to develop a relation between delta V and delta T. But in case of turbulent boundary layer, Prandtl number becomes insignificant. Do you understand it? In case of turbulent flow or turbulent boundary layer, Prandtl number becomes insignificant. The value of Prandtl number does not become 1, but Prandtl number does not decide the growth of velocity and thermal boundary layer when the flow becomes turbulent. There will be equal, because of mixing dominating, there will be equal growth of laminar as well as thermal, equal growth of velocity as well as thermal boundary layer. I hope this is clear. There is a boundary layer exists, but growth of velocity boundary layer and thermal boundary layer will be same in case of turbulent flow. Boundary layer will exist in laminar flow also, boundary layer will exist in turbulent flow also. I hope this is clear, isn't it? Yes. And these are some of the important formula you should take care of. The variation of h with x and local drag coefficient with x is same. Hx is directly proportional to x to the power minus 1 by 2 and Cfx is also directly proportional to x to the power minus 1 by 2. As x increases, we can say as x increases, Hx will decrease and Cfx will also decrease. As x increases in laminar boundary layer, Hx and Cfx both will decrease. The next question on your screen. The next one. Try to solve the next one. It is again MSQ. Couple of answers I have already given you. Delta X for laminar flow over a flat plate, it means external flow. This is for external flow. Laminar flow over a flat plate, external flow. Turbulent flow in pipe. Sorry. In pipe. This is internal flow. This is also internal flow. So delta X is not proportional to X. Delta X is directly proportional to under root of X. In case of laminar boundary layer, delta V or delta X, one and the same thing, is given by 5x upon under root of Rex. So it will be directly proportional to root X. And for laminar flow over a flat plate, delta X by delta T is given by Prandtl number to the power 1 by 3. That is correct. And for turbulent flow, I have not talked about the turbulent flow yet. For turbulent flow, delta X is given by x to the power 4 by 5. And Nusselt number is constant if the flow is, sorry, it was correct, na? This is also external flow. Laminar flow over a flat plate. And this is internal flow. In case of internal flow, Nusselt number is equal to constant. And the value of constant will be 4.36 for constant wall heat flux condition, and the value of constant will be 3.66 if the surface temperature of the pipe is constant. So B, C, D all are correct. B, C and D are correct answer. So if we talk about the turbulent boundary layer, for the turbulent boundary layer over a flat plate, turbulent boundary layer, when the local Reynolds number is greater than 5 into 10 to the power 5, then first formula is delta V is equal to delta T is equal to 0.376 x upon Rex to the power 1 by 5. So from here we can say delta V is equal to delta T is proportional to x to the power 1 minus 1 by 5. That is 4 by 5 or 0.8. The second formula is for local drag coefficient. For turbulent boundary layer, Nusselt number is proportional to, we can say Nusselt number is proportional to Reynolds number to the power 4 by 5 into Prandtl number to the power 1 by 3. That is for turbulent boundary layer. And Cfx is equal to 0.059 upon Rex to the power 1 by 5. That is for turbulent boundary layer. So from here we can say Cfx is proportional to x to the power minus 1 by 5. And CD, average drag coefficient, is 5 by 4 into Cf at x is equal to L. Then another formula, Nusselt number, local Nusselt number, that is Hx into x by thermal conductivity of the fluid, is given by 0.03 into Reynolds number to the power 4 by 5 into Prandtl number to the power 1 by 3. Can you develop a relation between Hx and x? Are you getting? Hx and x are related with x to the power minus 1 by 5. And H bar, average convective heat transfer coefficient, is 5 by 4 into H at x is equal to L. Similarly, average Nusselt number is equal to 5 by 4 into Nusselt number at x is equal to L. These are for turbulent boundary layer over a flat plate. These are the formula for turbulent boundary layer over a flat plate. Now let us move to the, is this clear? So it has nothing to do with the Prandtl number. The velocity boundary layer and thermal boundary layer has nothing to do with the Prandtl number if the flow is turbulent, or the boundary layer is turbulent when the Reynolds number is greater than 5 into 10 to the power 5. B, C, D are the correct answer. Yes, Pejal World, Vinay, well done, good. There is the next question on your screen. Now we will talk about the internal forced convection. When do we call the forced convection to be internal? That is flow in a pipe or flow in a duct. Whenever the fluid is flowing in a pipe or the fluid is flowing in a duct, it becomes the internal forced convection. So we define the bulk mean temperature. What is the expression for bulk mean temperature? So the Reynolds number is defined as rho into average velocity into hydraulic diameter by mu, or we can say average velocity into hydraulic diameter by kinematic viscosity. That is Reynolds number based on hydraulic diameter. And what is hydraulic diameter? Hydraulic diameter is given by 4 into A by P. For non-circular pipe, if the pipe is non-circular cross section, if the pipe is having a non-circular cross section, then we define the hydraulic diameter, where A is the flow area and P is the wetted perimeter. A is the flow area, then P is the wetted perimeter. And if the pipe is already circular, then for a circular pipe, DH will be equal to D, actual diameter. In that case, Reynolds number is rho into average velocity into D by mu, or V average into D by kinematic viscosity. That is how we define the Reynolds number for internal forced convection. And there are two terms defined. One is the average velocity. We can say mass flow rate, that is equal to rho into A into average velocity, should remain constant. The flow of mass through a particular section remains constant. So rho into dA into U, which is a function of R, remains constant. If you analyze this, we can say A is equal to pi R square for circular pipe, dA is equal to 2 pi R into dR, and U will be a function of R. If you put these values, then the average velocity, density will get cancelled out. Then the expression for average velocity at any section is 2 by R square integration of 0 to R U into U is a function of R into R dr. Similarly, the heat flow rate remains constant. What is heat flow rate? Mass flow rate, that is rho A into V average into Cp into Tb mean temperature should be equal to integration rho into dA into U into Cp into T remains constant. If we put all these value, T is also a function of R. If you put the value density getting cancelled out, Cp and Cp getting cancelled out, the rate of heat flow must remain constant from the section. So from here we can define Tb is equal to 2 by V average into R square, integration of 0 to R, U into T into R dr. That is called as bulk mean temperature at a particular section. If you do not remember the formula, you can develop the formula. One is equating the mass flow rate and another expression is equating the heat flow rate at a section. So what will be the correct answer for this one? What is the answer for the previous question then? Can you find out the answer? It will be 2 by R square. It will not be C. Pagel world, it will not be C. It will be A. The difference between A and C is only the numerator. A is the correct answer. If the average velocity and local velocity are same, if average velocity and local velocity are same, then option B would have become the correct answer. If local velocity and average velocity become equal, V average becomes equal to U. Then option B would have been the right answer, right? Is this clear? Now we talk about the energy conservation equation. Now if we talk about the energy equation, if there is a pipe and if there is a fluid flowing, here the temperature is TB1, here the temperature is TB2, and there is a continuous heat flow. This is the direction of heat flow and this is the direction of fluid flow from inlet to outlet. Fluid is flowing from inlet to outlet. So if we apply the energy conservation equation, according to energy equation, we can say the rate of heat flow will be equal to H into pi dl, area available for convection, that is peripheral area, into bulk temperature difference, is equal to change in internal energy of the fluid, mass flow rate into Cp into Tb2 minus Tb1, mc delta T. That will be the energy conservation equation. And what is delta T here? Delta T is equal to Ts average minus Tb average, and where average value of Tb is equal to Tb1 plus Tb2 by 2. And if it is laminar flow, if the flow in a pipe is laminar, when do we have the flow to be laminar? When the Reynolds number is less than 2000. When the Reynolds number in the pipe is less than 2000, then Nusselt number, which is defined as HD by Kf, is equal to constant. And the value of constant will be 4.36 for constant wall heat flux condition, and the value will be 3.66 for surface temperature to be constant. So from here we can say H is inversely proportional to d to the power 1 by 2 for laminar flow. H is inversely proportional to d to the power 1 by 2. And if the flow is turbulent, when the Reynolds number, that is rho into average velocity into d by mu, is greater than 4000, then the flow will become turbulent in the pipe. And if the diameter is not, if the pipe is not circular, then we use the hydraulic diameter. So for this, Nusselt number is directly proportional to, again, Reynolds number to the power 4 by 5 into Prandtl number to the power 1 by 3. Similar to turbulent flow, if the expression is similar to turbulent boundary layer. The expression is quite similar to turbulent boundary layer, and more specifically, Nusselt number is H into D by Kf is equal to 0.023 Reynolds number to the power 4 by 5 into Prandtl number to the power 1 by 3. So H is proportional to D to the power minus 1 by 5. That is turbulent flow in a pipe. That is the expression for turbulent flow in a pipe. So can you guys solve the question on the screen? Can you get me the answer for the question on the screen? If anybody is having any doubt, you can always let me know. For laminar flow over a flat plate, Nusselt number is proportional to, when do we have laminar flow over a flat plate? When the Reynolds number is less than 5 into 10 to the power 5. External forced convection. So Nusselt number is proportional to Reynolds number to the power 0.5. into Prandtl number to the power 1 by 3. For turbulent flow over a flat plate, when the Reynolds number is greater than 5 into 10 to the power 5, then 1 to 1. Laminar flow in a pipe, when the Reynolds number is less than 2000. The Nusselt number is constant. The value can be 4.36. The value can be 3.66 depending on the condition. If there is a turbulent flow in the pipe, we generally use 0.4. It can be 0.3. It can be 0.4 depending on whether the surface temperature is more than the fluid temperature or the fluid temperature is more than the surface temperature. So we can have this to be similar to 3. So A2, B1, C4, D3, isn't it? So these are the expressions. So are you guys aware that we are going to start MSQ series? So many students are having difficulty in MSQs, right? And because of the recent inclusion of MSQs, and there is an increase in MSQs in recent years, we have decided to start one series for all type of MSQ questions, which can help you to boost up your confidence in MSQs and to get the best possible score in your GATE 2024 examination. And the series is going to be started from 8th of August, this month only. So do not forget to subscribe our BYJU'S YouTube channel so that you get all the updates about the sessions in this MSQ series. All right, and share this information to all your friends as well. Shall we continue then? Anybody is having any doubt, you can just let me know. Now let us move to the natural convection. Let us move to the natural convection. Here there is a number defined that is called as Grashof number. What is Grashof number? In natural convection, Grashof number replaces the Reynolds number. In place of Reynolds number, there is a Grashof number. So Grashof number is the ratio of buoyant force to viscous force. What is the Reynolds number? Reynolds number is the ratio of inertia force to viscous force. Reynolds number was the ratio of inertia force to viscous force, whereas Grashof number is the ratio of buoyant force to viscous force. If we develop the expression, it is rho square g beta delta t x cube by mu square, or we can write it as rho square, mu square by rho square can be written as kinematic viscosity square. So Grashof number can also be written as g beta delta t x cube by nu square, where what is beta? Beta is called as coefficient of thermal expansion, that is 1 upon film temperature. The unit is Kelvin inverse. For an ideal gas, beta is 1 by film temperature, and film temperature is equal to Ts plus T infinity by 2. That is natural convection, where the buoyant force and density gradient plays an important role. Density gradient and buoyant force. What is the answer? What is Grasov number? G beta delta T x cube by nu square. C is the answer. C will be the correct answer for the Grasov number. Right? And beta is called as coefficient of thermal expansion or volumetric expansivity. Beta is called as coefficient of thermal expansion, or we can call it as volumetric expansivity. It is a thermodynamic property. It is a thermodynamic property. So in case of natural convection, we can say Nusselt number is a function of Grasov number multiplied by a function of Prandtl number. That is the, and Nusselt number we all know, H into x by kf, that is Nusselt number. Prandtl number we all know, Prandtl number is equal to kinematic viscosity by alpha, that is mu into Cp by kf for natural convection. And the Grasov number decide the nature of convection. What is LC? X is the characteristic length, where X is the characteristic length, where X is called as characteristic length, where boundary layer, the length where boundary layer is allowed to grow in case of natural convection. Allowed to grow in case of natural convection. There is a growth of boundary layer in case of natural convection. There is a growth of boundary layer in case of natural convection. Right? Yes. Where the boundary layer is allowed to grow in case of natural convection. And we can say Nusselt number is directly proportional to Grasov number into Prandtl number to the power 1 by 4 for laminar boundary layer. For laminar boundary layer, when the Grasov number is less than 10 to the power 9, and the value of Nusselt number is proportional to Grasov number into Prandtl number to the power 1 by 3 for turbulent boundary layer, when the Grasov number is greater than 10 to the power 9. Right? And product of Grasov number into Prandtl number is equal to Rayleigh number. The product of Grasov number and Prandtl number is Rayleigh number. So can you solve this one? There is a question on the screen. Can you get me the answer for this one? For natural convection or free convection, for natural or free convection, which one of the following options is correct? For turbulent, it is 1 by 3. For laminar, it is 1 by 4. For laminar boundary layer, it is 1 by 4. For turbulent, it is 1 by 3. For laminar, it is 1 by 4. For turbulent, it is 1 by 3. C is the correct answer. Yes, Naruto, well done. Yes, Pajal World. Good, good, good. C is the right answer. So that is all about our convection. All the important formula I have discussed for convection. Very, very important topic. And you can expect the direct formula based numerical question or the theoretical question in your ISRO examination. Complicated questions are rarely asked from the convection. And other than this MSQ series, we are going to start another series for ESE preparation. Complete questions of previous year, PYQs for prelims. Last 3 years PYQs will be discussed on this BYJU'S YouTube channel only from 14th of August 2021, 2022 and 2023. The series is going to be started from 14th of August. Now let us move to the radiation mode of heat transfer. Now let us move to the radiation mode of heat transfer. Can you let me know the formula for this radiation shape factor F122? Can you let me know the value of F122? What is the mathematical formula for F122? Yes, everyone. The shape factor. There is an important parameter in analysis of radiation that is called as radiation shape factor. So what is radiation shape factor? F122 is equal to Q122 upon Q1. The ratio of radiation leaving from surface 1 and receiving 2 to the total radiation leaving from surface 1. That is the shape factor 122. Q1 is equal to E1 into A1. Emissive power of surface 1 into area of surface 1. And emissive power can be written in terms of intensity, pi times of intensity into A1. That is Q1. We can put the value of Q1 from here. And how to find out Q122? Intensity of radiation is given by delta Q122 divided by dA1 cos theta 1 into dA2 cos theta 2 by R square. This is the intensity of radiation. So if we want to find out Q122 from here, then it will be intensity, then double integration A1 A2, then double integration A1 A2 multiplied by dA1 cos theta 1 into dA2 cos theta 2 upon R square. So if you put the value of Q122 here, so F122 will be equal to, so we can say F122 is equal to, numerator will be intensity, then dA1 cos theta 1 into dA2 cos theta 2 upon R square, and the denominator will be intensity into pi times of into A1. So if we simplify this, then F122 is equal to 1 upon A1, then there will be double integration A1 to A2. This will be dA1 dA2 cos theta 1 cos theta 2 upon pi into R square. That is the formula for radiation shape factor F122. If we want to write F221, then it will be intensity, then double integration, it will be dA2 cos theta 2 into dA1 cos theta 1 upon R square, divide by In into pi into A2. Intensity getting cancelled out. So F221 is equal to 1 upon A2, then double integration A1 and A2, then dA1 dA2 cos theta 1 cos theta 2 upon pi into r square. These are the formula for F122 and F122. So F122 is not equal to F221, but A1 multiplied by F122 is definitely equal to A2 multiplied by F221. That is known as, it is called as reciprocity theorem. Are you guys aware of reciprocity theorem? So the answer will be option C. Isn't it option C? Option C is the right answer. Option C will be the correct answer. Some other, C will be the correct answer. Some other expression, we can say F121 self shape factor is 0 for a convex surface and for a flat surface, but the self shape factor is not 0 for a concave surface. And for enclosure theorem, according to enclosure theorem, we can say F11 plus F122 up to F12n will always be equal to 1. F221 plus F222 plus F22n is equal to 1, so on. Fn21 plus Fn22 plus Fn2n will be equal to 1. These are known as enclosure theorem. Right? These are called as enclosure theorem for shape factor. For shape factor algebra. And another expression, alpha plus rho plus tau is equal to 1 for any surface emitting any type of radiation. For the any radiating surface. And for thermal radiation, tau is almost 0. Tau is taken as 0 for thermal radiation. Tau is taken as 0 for thermal radiation. There is no transmission of thermal radiation. That is why thermal radiation is called as surface phenomena. In case of thermal radiation, tau will be 0. So we can say alpha plus rho is equal to 1 in case of thermal radiation. There is a question on the screen. Then there are some important radiation laws. Can you let me know the answer? In list 1, there are some radiation laws, and in list 2, the expressions of these mathematical expressions for these radiation laws are given. Stephen-Boltzmann law. Let me first talk about some radiation laws. There is a law called as Planck distribution law. It is about the monochromatic emissive power of a black body. Planck distribution law. Then Stephen-Boltzmann law, also called as 1/4 power law. That is for EB, which is integration of E lambda B into D lambda. That is the total emissive power of the black body, which is area under spectral distribution curve on lambda axis, and that is given by sigma into T to the power 4. The third one is Wien displacement law. The third one is Wien displacement law. Lambda max into temperature is equal to constant, that is 2898 micrometer Kelvin. 2898 micrometer Kelvin. Micron into Kelvin. So lambda max. What is lambda max? The value of wavelength where the emissive power or monochromatic emissive power becomes maximum. Then the next one is Kirchhoff's law of radiation. That is valid for all the surfaces. And according to this, alpha is equal to epsilon if the system is in thermal equilibrium with its environment. And finally, Lambert cosine law. The intensity in any direction is proportional to cos theta. Theta is angle with the normal. With normal. These are some of the laws. So if we talk about Stephen Boltzmann law, that is 1/4 power law or 4th power law. Stephen Boltzmann law for emissive power of the black body, A4. Wind displacement law, lambda max is equal to lambda max into temperature is constant, that is 2898 micrometer Kelvin. B3, Kirchhoff's law is epsilon is equal to a good emitter is a good absorber. For a black body, emissivity is equal to 1 and absorptivity will also be equal to 1. So C1. And Lambert cosine law is about the intensity of radiation in any direction. It is given by I n cos theta, that is 2. 4, 3, 1, 2 is the correct answer. And finally, let us have a quick revision about the analysis of radiation using the circuit diagram. Can you find out the answer to this one? Analysis of radiation using the circuit diagram. Formula for radiation surface resistance. There are two types of resistances, thermal resistances for radiation. What is the formula for surface resistance? The unit of surface resistance is meter to the power minus 2. 1 minus epsilon upon epsilon A. A is the area of the surface, epsilon is emissivity. So for surface resistance to be 0, the body is called a black body. The body can be called as black body when the surface resistance is 0. So when the surface resistance is 0, when either epsilon is equal to 1 or A is infinite, either of these cases will make the body to be the black body. Emissivity is equal to 1, either the emissivity is equal to 1 or area is infinite, and this is called as radiation space resistance. 1 upon A1 upon A1 to 2 or 1 upon A2 F2 to 1 is called as radiation space resistance between 1 and 2. 1 and 2. So there are two types of resistances. One is, so our surface lies between 0 and infinity. When it is 0, it is the black body, and surface resistance is infinite, the surface is a white body. Radiation space resistance between 1 and 2, we can also call it as R1 to 2 or R2 to 1, is given by 1 upon A1 F1 to 2. The unit is still meter to the power minus 2. So these are the resistances. So whenever we talk about the radiation exchange between the black body, net radiation exchange between the black body. For the black body, there are two resistances only. So Q122 net for a black body. If we talk about the black body, surface resistance will be 0. So Q122 net will be equal to delta EB upon, there will only be space resistance R1 to 2, or we can say sigma into T1 to the power 4 minus T2 to the power 4 upon 1 upon A1 F1 to 2. That is joule per second. That is the radiation exchange between the black bodies. Right? This RS is the space resistance. Either we call it as R122 or R221, or we can also call it as 1 upon A2 F221. These are the space resistance. For the non-black bodies, that is the net radiation exchange. Radiation heat exchange. And for the non-black body, if we talk about the non-black bodies, surface resistance is non-zero, space resistance is also non-zero. So Q122 net for the two non-black bodies will be equal to delta EB, then space surface resistance for body 1, space resistance between 1 and 2 plus the surface resistance for body 2. Or if we put the value, then we can write sigma into T1 to the power 4 minus T2 to the power 4 divide by 1 minus epsilon 1 upon epsilon 1 A1 plus 1 upon A1 F122 plus 1 minus epsilon 2 upon epsilon 2 A2. This will be the expression. Or we can also write it as Q122 net. For the non-black bodies, we can write sigma into A1 T1 to the power 4 minus T2 to the power 4 divide by 1 minus epsilon 1 upon epsilon 1 plus 1 upon F122 plus A1 by A2 into 1 minus epsilon 2 upon epsilon 2. This is the expression. And that can be equated with sigma into A1 into Fg into T1 to the power 4 minus T2 to the power 4. This Fg is called as, what is this Fg called? This is called as gray shape factor. Fg is called as gray shape factor, or it is called as equivalent emissivity, or it is called as interchange factor. By equating these two, we can find out the value of Fg, interchange factor. So this expression can be modified for different situations. This expression can be modified for different situations. One is infinitely large parallel plates. If there are infinitely large parallel plates, A1 is equal to A2 is equal to A, and F122 is equal to F221 is equal to 1, because F11 is equal to F222 is equal to 0. Infinitely large parallel plates, Q122 net will simply be sigma into A into T1 to the power 4 minus T2 to the power 4 divided by 1 upon epsilon 1 plus 1 upon epsilon 2 minus 1. For concentric cylinders, A1 is equal to 2 pi R1L and A2 is equal to 2 pi R2L. For concentric cylinders, F11 is equal to 0, F122 is equal to 1. Inside cylinder is having 0 shape factors. So Q122 net is equal to sigma into 2 pi R1L into T1 to the power 4 minus T2 to the power 4 divide by the expression will be 1 upon epsilon 1 plus R1 by R2 into 1 minus epsilon 2 upon epsilon 2. And for concentric spheres, that is area is equal to 4 pi R square. Here also F122 is equal to 1 because F121 is 0. For convex surface, self shape factor is equal to 0. So Q122 net is given by sigma into 4 pi R1 square into T1 to the power 4 minus T2 to the power 4 divide by 1 upon epsilon R1 square by R2 square 1 minus epsilon 2 upon epsilon 2. And a small body in a large enclosure. That is A1 by A2 is almost 0. Then Q122 net will become sigma into A into T1 to the power 4 minus T2 to the power 4 upon 1 upon epsilon 1. A1, or we can write sigma into A1 into epsilon 1 T1 to the power 4 minus T2 to the power 4. So here the gray shape factor is equal to epsilon 1. The gray shape factor. These are some of the important standard results. You should remember them. Yes, can you get me the answer for this one? Based on the previous analysis, can you find out the answer to this one? Yes, a small object in a large cavity, that is given by this expression A2. Infinitely large parallel plates, I have already shown you, B1. Infinitely long concentric cylinders, so it will be R1 by R2, this is C4, and concentric spheres, it will be R1 square by R2 square. 2143, yes, A2. No, it will not be C3D4, it will be C4D3, isn't it? There is a square. Here A1 will be equal to 4 pi R1 square. Here A1 is equal to 2 pi R1L. That is the difference. So 2143 will be the answer. Isn't it? Now let us talk about the radiation shield. The final expression is for a radiation shields of emissivity epsilon 3. Of emissivity epsilon 3. So Q net with N radiation shield is given by sigma into A into T1 to the power 4 minus T2 to the power 4 1 by epsilon 1 plus 2N by epsilon 3 . It will be 2N by epsilon 3 plus 1 upon epsilon 2 minus N plus 1. This is the expression where A1 is equal to A2 is equal to A3, that is A, or we can say F1 to 2 to 3 is equal to F3 to 2 is equal to 1. Shape factors are 1 and N is the number of radiation shields having same emissivity. All are having same emissivity, epsilon 3. N is the number of radiation shields having the same emissivity, epsilon 3. And if we take a special case, epsilon 1 is equal to epsilon 2 is equal to epsilon 3 is constant, that is epsilon, then Q for N shield will be equal to 1 upon N plus 1 into Q without shield. So the ratio Q for N shield divided by Q without any shield is 1 upon N plus 1, where N is the number of shields. If the emissivities are same for each and every surface, N is the number of shields. So can you let me know the answer to this one? And that completes our discussion. What is the ratio for N radiation shields with equal emissivity? What is the ratio of N shield to the without shield? What is the answer? Yes, definitely the answer to this question is option C. So that is all from my side, guys. I hope you enjoyed this session and were able to revise the important formula which can help you to get the best possible score in your upcoming ISRO examination. If you have anything to discuss, any doubt, you can always connect with me through the mail ID or you can join me on the Telegram. Thank you guys for joining in and taking interest in the session. It could not have been possible without your involvement and without your participation. So this is all from my side. There are important series which are running on our YouTube platform, Sunday Ka Funda series as well as Super Saturday series. Please do not forget to like and share this session and do subscribe our BYJU'S YouTube channel. So thank you very much. See you in the next session. And today at, I don't know the timing, there is another series which is running for GATE 2024 aspirants. We are discussing the questions from the thermodynamics. Timing for today's session is maybe around 6:30 to 7. I will share the information to my Telegram channel. All right. That is all from my side. See you in the evening. Till then, enjoy. Take care. Have a good day and a great career ahead. Jai Hind.